All right, thank you. I hope you can hear me, and I hope you can see my screen. So, yeah, I know that. First of all, I hope that you all had a good practice session, and secondly, I know that I'm talking like in the context of a programming contest, and that in a programming contest, perhaps sometimes you're tempted to adopt a little bit of let's say flexible relationship with correctness, perhaps, and in order to like perform well under the time pressure. But one of the things that I'm personally so interested in, or one of the reasons why I'm interested in functional programming in Haskell, is that it is allowing you to, with little effort, write like relatively correct programs, and that you have a strong type system that supports you. And personally, I feel like even more so in a stressful situation when there is little time and I have to get things right, I like to trust the type system. So today I'm going to give this talk on true lies and false truths, on the importance of evidence in programming, and I'm going to show you something that I find quite important in programming, and I hope you like the idea as well. I'm going to show this in the context of Haskell, but it is applicable to essentially all of programming. It is perhaps not as easy to use in some languages that don't have the necessary concepts, because really, as it turns out, the important things we're going to use are the notion of sum types, or more generally algebraic data types, and pattern matching. So those are the basically two important concepts here. So let's have a look at a simple test. So this, let's just assume you have a function isValidEmail that goes from a string to a bool. So the idea is that you check a piece of text whether it's at least a syntactically valid email address, and then the outcome is either true or false, depending on whether that is the case. And if you have such a test, you can use it in a piece of code that could look roughly like this. So you have some piece of code, and the first thing you're doing is you're reading some untrusted input from somewhere. I mean, can be a file, can be a database, can be the keyboard of the user or something, and then you get a piece of text, and then you're running your validation function on this piece of text to check whether it's a good email address. And if the outcome of the test is successful, then you go on and do some other stuff with this piece of text. And otherwise, I don't know, perhaps you're like reading more input, or you're printing an error message, or something like that. Okay, and then you go on into some other function that takes a piece of string, a string as an input, but you're expecting it to be a syntactically valid email address at this point. And sooner or later, you're actually going to perhaps send an email where it becomes really important that you're using a syntactically valid email address, at least, right? And other things may become important as well. But this is not ideal code, right? Because first of all, at this point, from the perspective of some other function here, we can never truly be sure whether this email address has actually been validated, right? I mean, we're getting a string, and the string could be anything. There is nothing that the type system does to enforce that it is an email address. We could write it down in the comments. Please make sure that you're calling this with a valid email address, right? But nevertheless, there's always a nagging feeling that like, have we validated this? Is it good? And we could do it again, right? So the temptation would be to like compensate for that by like running isValidEmail again right here. But then perhaps we are like scattering lots of redundant validation efforts all over the program text, right? So that's not really ideal either. And if we try to look very carefully, what really the source of this problem is that we have performed this test here, and we're getting a Boolean out. And while to us as human readers, perhaps true has a certain meaning and false has a certain meaning, in terms of the type system and what the computer knows and what we can reliably work with, we haven't actually learned anything from the outcome of this test. Because a Boolean is either false or true, and both these values are like qualitatively the same. There are different values, okay, but they have the same type, and they're interchangeable without like breaking the program in the sense that the compiler will reject it, right? So it's very easy to make mistakes. And so forgetting the test here, for example, and just calling some other function on txt immediately would still have the program work in the sense that the compiler will still accept it. Running the test twice will still have the program work. So the conclusion here is that the Boolean is the problem. So Booleans considered harmful in this talk, and I'm going to show ways to like do better. What can we do in order to do better? We want a test which actually allows us to learn something from the outcome, right? And learn something not just as the human user, attaching some meaning to these labels true or false, but learn something in such a way that the compiler, that the type system of the language can actually work with this. Okay, and the solution here is to provide evidence. Evidence, in this case, of the successful test outcome. So rather than returning a Boolean, we're going to return something of a maybe type. So this is a data type declaration in Haskell that says for every type A, we can form a type maybe of A. And there are two possible shapes of values in the type maybe A. One is called nothing. So nothing is a constant of this type that signals failure. And you can think of it as a new name for false. So that is what we're going to use if a test is negative, right? And just A, so just takes an argument of some type A as and then forms a value of this maybe A type, right? Just signals success, but it takes a value of some type. So this replaces true, but unlike true, it actually carries some piece of evidence. And the idea is that this evidence gives us a handle for like the successful outcome of the test that we can actually rely on. So how does it look? So our old isValid email function had the type string to bool, and we're now going to change this type into string to maybe of email. So rather than just saying yes or no to a given string, our function isValid email now has like two options still. It can fail the test, and in this case, we will return nothing. Or it can pass the test, and in this case, it will actually transform the input string into a new type, which we call email, and will return just of that transformed email. And now, if we look at the same piece of code, we can still read a piece of input and we get a string, and we can call our new isValid email function on that piece of string. And now we're not using an if then else, but we're using a so-called case expression where we're saying we want to match on the result of this test. And there are two options. There are still two options. One is that the test failed, which is this nothing case, in which case we are still going to like do something like print an error message or recover from the failure somehow. But in the successful case, we now get access to the transformed piece of text that is the evidence of the successful outcome. And this variable email here has type email now and not string. And we can go on and call some other function on this variable of type email. And then indeed some other function is now going to take an email rather than a string, which is a new type and a different type. And the good thing is that in here, just by using a different type, we know as the programmer that we have already performed this test, right? We no longer have to wonder, did I run this test or did I not? just by the fact that I'm getting something that is not of type string, but of type email, I know that, well, yeah, I have to run some validation on it, because presumably there is no other option of actually producing a value of this type than to run a function such as this that actually checks that some input is a valid email address. So here we can no longer forget to run the test, because if we would just call some other function with txt, it would not be type correct. And in here, down here, we can rely on the check having happened because we have something of the evidence type. All right, so let's summarize. Before all this, we had something where the test outcome was a Boolean. And the problem is that to the type system, the two values of a Boolean are completely interchangeable. False and true you can interchange them in your program, and your program will still type check. So it's very easy to forget a test, and it's very easy to run a test unnecessarily often if you're paranoid and want to overcompensate. Afterwards, we've changed the test outcome to maybe of some new type, where that something is evidence. So the successful outcome of a test now provides evidence. And we have replaced the if then else, which is symmetric, and we can flip both branches and it will still work. We have replaced that with a case of expression, where we have two branches, and only in the case for the successful outcome, we actually get access to this evidence, which we can then use to pass it on to other functions, which can then rely on the fact that we have actually performed the test. Okay. So by the way, I'm quite happy to get questions during the talk, and I'm occasionally going to ask Unar whether any questions have accumulated. So I mean, if that's the case already.
So far there are no questions.
Okay.
To you.
Okay. That's
just
good.
Keep going, and hopefully you'll get some questions.
Yeah, I mean, by all means. I mean, if you want me to clarify anything, then just ask on the YouTube live stream, and Unar will forward the questions to me. Okay. So so that's that was the first example I wanted to go through, and that is like basically conveying the main idea. But now I want to show a couple additional examples that go into a bit more detail and see that this idea is more widely applicable. And there is one thing that I have been kind of glossing over so far, namely that I have, like, it's relatively clear if you look at is valid email of type string to bool, it's relatively clear how you would write this, right? So you would implement some kind of check that would check whether the string is of the right shape, and depending on that you say true or false, right? But now if we introduce a result type like this, then what is this type email? And like, sure, if we implement the function and the check fails, then saying nothing is still very easy. But if we have to provide some kind of evidence, what is this evidence? How does it look like, right? So I haven't said that yet, and that is one missing piece. And I'll get back to that. But I first want to look at a number of other examples. Okay. So let's look at a different example. And so this is perhaps a typical Haskell example, but nevertheless, I mean, so here we have a list of integers, and we want to sum up all the elements of that list. So we compute a single integer out of that. And one way to implement this function in a functional language, if you have some kind of list data type, is if you have a function IsEmpty that takes a list and checks whether it is empty, yes or no. And if the list is actually empty, then we return 0 as the sum of integers in that list, because the neutral element of addition is 0, right? So 0 makes sense as the sum of an empty list. And if the list is not empty, then we use the function head to get the first element out of this non-empty list. And we use the function tail to get all the other elements out of the non-empty list. And this function tail returns another but shorter list. And then we can use recursion on the shorter list to sum up all those elements, and finally add the first element on top. And together we'll get the sum of all the integers in the list. Right? And that is a nice recursive definition. And we're assuming here that we have a function IsEmpty that performs a test whether a list is empty. And we're assuming that we have functions head and tail, that if we have a list of elements of some type A gives us the first element of that list. And this function head is assuming that the list is non-empty. And the function tail is assuming also that the list is non-empty and basically drops the first element and gives us the list of all the other elements of that. And again, we have kind of a similar problem as in the first example, right? Because, so for example, what happens if we accidentally flip the two branches in this if then else? If we accidentally write if IsEmpty list, then head list plus some list of tail list L0, then the compiler will still accept this piece of code, right? Because our IsEmpty test is producing a Boolean. And as I said before, false or true are, as far as the type system is concerned, of the same type. They're completely interchangeable. So flipping the two branches in this case, in this if then else, will not lead to a compile time error. It will lead to a crash. The moment we are starting to actually run this on any kind of list, well, actually, it depends. I mean, if we run this, if IsEmpty is implemented correctly and we flip the two cases, and we're running this on a non-empty list, then we're just going to get the wrong result because we're suddenly getting 0. And if we're running this on an empty list, we'll actually get a crash because suddenly we're calling head and tail on an empty list, and our program will crash. Now, this is all nice and well as long as we do a lot of testing, but in large programs, right, if you have these kind of things hidden somewhere, like really testing every single code path is often difficult. And also, this is a nice example still because head and tail, the calls of head and tail, are relatively close to the actual test, right? But you can envision a different situation where you perform a similar kind of test, like whether a list is empty or not, and then you pass the list on that you have tested for quite a while to other functions, and you're still having this implicit assumption that the list is non-empty, but it's very easy. Perhaps you have like modified the list in between, or you've done some other operations. It's very easy to kind of forget whether we've actually run the test and whether we can actually rely on it. Okay, so so that is like a similar situation as we have been in before, and we can try to again apply a similar solution. So again, the idea is that we provide evidence. Now this time I can be a little bit more concrete about what kind of evidence we want to provide, because what is suitable evidence that a list is non-empty? Well, that is exactly if we can give the first element and the rest of the list. That is exactly suitable evidence for a non-empty list. Because if we have the first element explicitly and the rest of the list, we can recover the original list because we have still all the information of the original list. But simply by having the first element, it makes it totally clear that the original list could not have been empty, right? And we would never have been able to obtain that first element if the list had been empty. So this function has a much more informative result type, because again, if the list is empty, we can produce nothing as the result. And if the list is non-empty, we can produce just of a pair of the first element and the rest of the elements. Okay, so and now if we rewrite some list, we again replace the if then else with a case of expression. which performs pattern matching. And in the case that the list is empty, we're now getting nothing rather than false, and we return 0. And in the case that the list is non-empty, we're getting evidence for that. Namely, we get the head and the tail, and this cannot fail, right? Because it's built into the test that we get the evidence that the list is actually non-empty. And so we can safely access, and this actually should not be 1+, but it should be head plus. So did I do this wrong in the other one as well? No, sorry. So this should be HD plus some list of TL, sorry. Okay, so you can still make other mistakes, as you can see. It's saving you from one kind of mistake, but you can still make other mistakes. But the good thing here is flipping the cases is now no longer possible, right? If I would write 1+ or even the correctly HD plus some list TL in the first branch, I would refer to out-of-scope variables. This would immediately give me a compile time error. I don't even have access to the head and the tail, right? And I no longer am at risk of potentially crashing either, because I'm no longer calling these unsafe, like select the head of a non-empty list or select the tail of a non-empty list function, because I have combined the testing with the fact of learning from the outcome of the test. So if you have seen functional programming languages before, and perhaps even have seen Haskell before, you will know that lists in Haskell are in fact defined as having this kind of structure. So if you look at the Haskell data type definition of a list, well, in Haskell, actually, lists are sort of built in and have slightly special syntax. But structurally, lists in Haskell look exactly like this, and you could define them like this if you wanted to. Lists are a parameterized data type of which there are two possible shapes. A list can either be empty, and then you can like give the name of that constructor nil. So that corresponds to sort of our nothing case, right? And the IsEmpty check. Or they are non-empty, and in that case, you have a first element and you have a rest of the list. This kind of inductive definition is in fact the basic definition of lists in Haskell. And then you can write some list, and again, I made, unfortunately, the same mistake here. You can write some list in exactly the way as before, only that you don't even need to run this IsEmpty check anymore. You can directly pattern match on the two constructors of the list type, but the same principle holds. You combine the test as to which shape the list has with the evidence that the test is successful or has actually had the outcome that you're expecting, because you're only getting access to the head and the tail of the list in the case that the list is actually non-empty. And this more generally shows that these concepts of sum types and pattern matching are quite powerful, and they're often a little bit overlooked. If you look at literature about Haskell or other functional programming languages, you'll find all sorts of things being said about like very fancy, very advanced features of the type system, like even more recent extensions. But actually, this idea that a data type can have multiple different shapes and that you can use pattern matching to distinguish between them, and that the different shapes can have different evidence attached to them, different payloads, and you only get access to the payloads of one particular shape if you're actually in the right branch. Right? This is called pattern matching. This is already quite old and has been in at least in functional programming languages for many, many years. And I think it is often not quite appreciated just how powerful this idea is, and that it is really a substantially better way of defining a function such as SUMList than using the if then else and the Boolean test that we have seen before. Okay, so this is another good point to ask whether there have been any questions at this point. Still not?
Still no questions.
Okay, well, that's good. I mean, I hope that
Either it's very clear or
I'm going to positively assume for the time being that this just means that it's all very clear. So here is yet another example, and so basically, in a way, I could say this example here is sum lists and so on. This is an example for something where Haskell gets it right, because I think most people in Haskell, and also if you look at the libraries that are out there, would write a function such as SUMList using essentially pattern matching rather than using in this first style that I presented here, right? So that that is something where I think basically Haskell already drives you into the right direction. But there are other situations where at least Haskell's base library actually, in my opinion, does not get it right, and it promotes a function that is not ideal. And one such example is filter. So filter is a cool function. It's an example of a higher order function, something you see a lot in functional programming languages. This is a function that is parameterized by another function. So the way to read this type of filter here is, there you have these many arrows, but you can actually look at it as a function taking two arguments. And the first argument of filter is itself a function that is a test that can run on elements of type A and gives you a Boolean result. So, so if you imagine you're ultimately interested in running this on a list of integers, if you have any kind of test on an integer, a function that checks whether an integer is even, or a function that checks whether an integer is 0, or a function that checks whether an integer is between 1000 and 2000, or something like that, or a function that checks whether an integer is prime, right? And if you have a function that that can check that and can give you a false or true result, then you can feed it into filter as the first argument. And then you also give it a list of integers. And then as the outcome, you get another list of integers that contains, well, and that's where the confusion in a way arises, because the name filter doesn't make it entirely clear. It contains the elements that pass the test, or the elements that fail the test, or which ones? So probably one of the two, right? But actually, I think just by looking at the name filter, it's not terribly clear, and you actually have to look at the documentation, or even better at the implementation, to be entirely sure. So so we've learned now we are going to use pattern matching on the structure of the list, so we're not going to make that mistake again. So we're going to look whether the list is empty, and if the list is empty, then clearly we're going to produce an empty list again. And if the list is not empty, then we're going to check using this given function f, which takes an element to a Boolean. We check the first element, whether it passes the test. And now we have two options, and we have to check, do we keep the element if it passes, or do we keep it if it fails? And the right answer, although there is no really right answer, but what the actual filter function in Haskell does is it keeps the elements that pass the test. So the definition looks something like this. And in the case that f of hd evaluates to true, we go to the then branch, and then we produce a new list that has hd as the first element. So hd is kept because it passed the test, and then we recursively filter the rest of the elements. And if the test fails on the first element, then we do not keep it, and simply we move on to the rest of the list and filter the remaining elements. Okay, but once again, it is it would be equally correct even. I mean, in this case, it's really a matter of agreement, right? And even the name doesn't even make it entirely clear to flip the cases, right? And you really have to know, and it's not obvious, and it's very easy to make mistakes. And that's something that I also actually see with people who begin programming Haskell, that they just accidentally flip the notion of filtering because they misunderstood which way around it is being intended. Okay. So again, it would be actually much nicer if we could somehow make that explicit. And again, we can apply the same idea. We can replace the Boolean outcome here with a maybe outcome. So rather than having function filter go from A to bool to list of A to list of A, we now say we are passing in a test that produces evidence of a successful outcome, right? So we have a function that can operate on elements of some type A, and it can either result in nothing, or it can result in just of some possibly changed type, which provides evidence for the outcome of for the successful outcome of the test. And then our function also goes from a list of A to a potentially different list of type B now. Now, if you have type variables and type signatures like this in Haskell, right, and it means it's a polymorphic function, it can be used at different types, and you're still allowed to use the same. You're still allowed to use the same type when calling the function. You can still say, I have a function that goes from int to maybe int, and then I feed it a list of integers, and I get a list of integers. That's fine. But you can also say, I'm taking something like my isValid email, my better isValid email check, right? And I pass in a list that goes from a function that goes from string to maybe email, right? And then I feed it a list of strings, and I'm getting back a list of emails. And that is better, right? Because if I'm getting back a list of emails from a list of strings, I'm actually immediately seeing that I've actually achieved something, right? That I've made progress. And it's not just me again, not just the human that is seeing it. It's also the computer in the form of the type system, and it can help you along to use this in the right way. So let's apply this, right? So let's have a concrete filtering. Let's see, look at a concrete situation where we might want to filter. So I already gave one example. One easy example is to check whether a number is even. So a classic check for whether a number is even would probably be implemented in terms of sort of a modulo function on integer division and getting the rest of an integer division. So if we have a mod function, which we have in Haskell, and we call mod I2, we want that to be 0. And this is an equality test. So and the equality test returns a Boolean. So this would be a classic check that something is even, that returns a Boolean. And then if we call filter evens and we check whether, like, we want to know in a list of integer, we want to keep all the even numbers in that list, we can just call filter with the even function on a list. But as I said, I mean, like, we have to know, like, does it keep the even numbers, or does it drop the even numbers? And the type does not change. We start with a list of integers, we end up with a list of integers. So again, this is not ideal, right? And we could also easily add a non-even integer again into that list afterwards, because there is nothing in the type system that enforces this list to contain only even numbers. So what's suitable evidence for a number being even? Well, actually, we can use an integer, but a different integer as evidence. So we can, like, define a data type even that has just one shape, and that only is intended to capture even numbers, but we just store the integer divided by 2, which must be possible without any reminder if the original number was even. So I've called this constructor here, or this shape, I've called this twice, because the idea is that if we have the value twice 4, for example, then it actually represents the even number 8, right? And if we have the value twice 21, then it represents the even number 42. And we couldn't represent an odd number if the idea is that whatever is in there is representing twice the number that is stored in there. And then we can write the even check to provide evidence like this by saying we go from int to maybe even, and we perform, this is a sort of a function, a variant of the function mod that I showed before, that performs an integer division and gives us back a pair of both the integer part of the division result and the remainder. So if the division by 2 actually succeeds without a remainder, then we know we do have an even number, and we can produce just of twice j, right? And otherwise, we know we don't have an even number, and then we produce nothing. And now, if we look at examples, if we perform an even check on 42, we get just of twice 21. And if we do an even check on 17, we get nothing, right? And now if we revisit the function filter evens, it still works as before, but it actually goes from a list of int to a list of even. And we can see on the type level again that we have actually successfully performed this check. And not only does that mean that we don't have to perform this check again, it also means that it's now no longer easily possible to just add an odd number to this list of even numbers, because then the compiler will also complain. Then I have to explicitly transform this list back into something that is more relaxed again, and then that is tracked in the type system as well. So these are really simple means of guiding ourselves, always just carefully nudging us into the right direction, and just cutting off lots of paths in the program that would lead to unnecessary errors. Okay.
Maybe a question from myself.
Yeah.
So this seems like maybe to some unnecessarily complicated for something so simple as checking or making sure that you have an even numbers. Do you have any examples of real life use cases where this actually starts making sense to use, where it helps, even though it makes it more complicated?
The first example is a very, very real life use case, right? And so if you and in general, that is really the real. I mean, thank you for the question. I mean, but that is really the real life use case where it matters in virtually all programs, right? That are interactive at all. You are at some point you're reading untrusted user input. You're reading some stuff from files. You're reading some stuff via the internet. You're reading some things from the database and so forth, and you don't necessarily, I mean, even the database, you don't know. I mean, sometimes things have been checked there, but you don't necessarily know that these are all pre-checked and trusted data. Okay, so you have a part of your program that has to deal with the fact that data is untrusted and unchecked, and this can come in many forms. So an email address is just one simple example. But it can be it can be all sorts. I mean, if you have any kind of database that you want to store. So say you have a programming contest task description, right? And you have a data type for that, and a programming contest task description is supposed to fulfill certain invariants. I don't know which ones exactly, but perhaps we have certain requirements. There should be at least 3 tasks and at most 10, and then they should have a sufficiently long description, and I don't know, the description should perhaps only contain certain characters and not certain others, and then perhaps there are some other constraints on this type as well, right? So you at some point when you have some external description format where you perhaps like make your task description available as a text file, or you submit it to a REST service as a JSON document, at some point you will perform additional validation on that input and say, like, does this fulfill all the invariants that I'm ultimately expecting for this piece of information to hold? And it is good if that boundary is clear, right? It is very, very bad if you are performing a check that is ultimately just giving you a Boolean. Because again, this is exactly the point that I'm making. This check then is not just easy to forget, but it also means that in all the other parts of your program, you have to always have this nagging worry, like, okay, I'm making these assumptions now, but can I really make these assumptions? And you're perhaps modifying, like your program is perhaps modifying these task descriptions as you go, right? And you would like to know that like the invariants are still adhered to, and sometimes you may need to recheck. So just by changing such a validation step from having a Boolean result to something that goes explicitly from some untrusted task description data type to maybe of a trusted task description data type, that makes it very clear where, like, whether you've run the check and how often you've run the check, and if you do anything that could possibly violate the invariant, you probably get out of that data type again, and then it's also very clear that you actually have to rerun the check. So this happens all over the place, right? And yet another example is like where you're perhaps not even dealing with exclusively untrusted user input, but still often you're doing some form of templating of say database queries or of HTML documents, right, where you are piecing together HTML pages from various individual pieces, and you have to perform some amount of validation that you have properly escaped all the critical characters in your string, and so on and so forth. And for SQL queries is even more important, right? So that you don't have some sort of expose yourself to some sort of injection attacks. And again, it's very, very helpful if all these transitions go along with type system transitions, where you're actually providing evidence of your transformation, so that you have a different data type for HTML documents, a different data type for SQL queries, that these are not just strings, and that you're guarding the boundaries with checks that actually provide evidence of the successful outcome. I think that that's sort of the real life transfer of everything that I'm talking about. And sure, I've been deliberately going from like a real life example first to smaller examples now to ideally drive the idea of providing evidence home in a simple setting where it's easy, where it's hopefully easy to understand what's going on, even though you may be right. I mean, in practice, you wouldn't do it for every single test, like for just checking whether numbers in a list are even. I would probably not do it myself either. It depends a little bit on how critical this is. But for real like important data types in your domain that you're implementing, I would absolutely do it, and I would do it nearly every time. Okay.
Right. So it's a type of sanitation for your data that can be verified at any single point in the program, rather than you specifically, like explicitly having to sanitize the data at every step. It's just, it happens naturally with...
It happens naturally at a clearly defined boundary, because the boundary is now visible, right? You can see by looking at the type signature of every single function, am I operating on untrusted input, or am I operating on trusted input? And it's not just something that you put in the comments as an informal prerequisite. I'm expecting this and this and this additional condition to hold. You're making it visible in such a way that the type system can track it for you and can check it for you. And that's the idea. I mean, in general, type systems are your friend, right? I mean, so this is like one of my general messages as well. I mean, like modern type systems and programming languages are so immensely powerful You should stop seeing them as just sort of this guardian that stands between you and success, that you have to fight and bash the compiler long enough to finally accept your program. You should really see them as an assistant in helping you, and this is one way of like making constructive use of a type system, because you're saying like, track for me whether I have done this check, right? Warn me if I haven't, whereas otherwise you would have to keep track of it yourself.
Great, thank you. I think that was a great answer. Okay. There's another question. Do you want to...
Just let me just briefly say, I mean, we started a bit late. Can we also end a bit late, or do I really have just 7 minutes left? I mean,
no, that's fine.
Okay, yeah, then just go ahead. Yeah, I'm happy.
It's from Ragnar. He asks if you see applications for this return of proof in imperative languages, and if we wanted to, we could do the same in C++, although it would be an uncommon pattern.
So I think really it would be, I think it's great to have this in every languages, but I mean, the idea applies to every language, right? Or the underlying problem applies to every language, that Booleans are just not dramatically expressive. But what you can do about it depends a little bit on what features you have in your programming language. And to make it convenient, right, I think you really need two language features. You need some types. You need to some types basically means you need the way that in a data type you can have different shapes and say this data type is either of this shape or of that shape, and like the different shapes can have different arguments attached to them. And then you need which basically goes along with that. You need a construct which can match on these different shapes all in one go, essentially as some sort of atomic dispatch to like which of the different alternatives something has been built by. And you can see that this is not something that you can only have in like purely functional languages, because so I mean Haskell and standard ML and OCaml, they all have this, but Scala has this as well in the form of case classes, and Scala is in a way a hybrid functional object-oriented language. Rust has this as well, which is not a functional language at all, even though like many functional programmers are like happy to use it because it like takes so many hints from recent programming language theory in its design. But Rust is certainly not a functional programming language, and it has all these features, so you can directly employ it in Rust. And I must say, I'm not totally familiar with all the other reasons. I mean, so for example, I have heard that Kotlin has some form of sum types, but I've also heard that it is basically cheating. I don't know. I mean, this is something where I haven't looked at in enough detail. And I'm sure in C++, which is a language which like has loads of features, you can encode stuff like this as well. The question is, does it become convenient enough, and does it become foolproof enough to ultimately really help you, or will it just replace one way of making accidental mistakes with another way of making accidental mistakes? That's something I can currently not judge because I just don't have enough active experience with C++. But in principle, the problem is universal to programming in general. And I think programming languages are adopting sum types and pattern matching more and more, among other things, for exactly this reason. Right. Okay, so yes, so okay, we were here actually. So so far we've only seen tests that were sort of like providing evidence of a successful outcome. But let me, like, if you bear with me sticking with this toy example for a bit, you can actually provide evidence of failure as well. And sometimes you actually want to not make such an asymmetric decision, but you really want to classify something into multiple, perhaps not even just two, but into multiple different options. And for each of them, you would like to have evidence of that particular option was actually the one that did occur. And this even example does actually allow us to show this, because like every number that isn't even is odd, and we can provide evidence for that as well by making yet again a different type, odd, that we use a number, again an integer, as evidence, but in such a way that 2 times that integer plus 1 represents the original number. So if we had 5 and we would call parity on 5, we would get a value of this odd type containing a 2, because 2 times 2 plus 1 is 5. And then we can rewrite our even function into a more general parity function that actually makes a decision between whether a number is even or odd. Right? So now we don't even just have a maybe type where we have, in the case of failure, we're still just saying nothing, but we're saying either it is an even number or it is an odd number. In both cases, we have evidence for whether the test succeeded or whether the test failed. And here we are now making a distinction as to whether the remainder is 0 or 1. And if it is 0, then we produce a left that is one of the 2 shapes of the either type, where we say twice j. And if we have this result here of the diff mod, then we say right. So that explicitly says that we want to produce an odd number. And then we use this twice plus 1 shape with j again. And the either data type in Haskell looks like this. It really gives us 2 options that are called left and right, and now they both carry evidence, and they carry evidence of potentially different types that that represent exactly the information that is needed in order to prove that that a test was successful, right? Or not successful, but that the test had the outcome that we claim it has, right? I mean, now it's no longer just about it being successful. And again, there is a function in the Haskell libraries that is kind of suboptimal, like similar to filter. By the way, the revised filter function that we had been defining is actually in the Haskell libraries as well, if you know where to look. It's called map maybe, but it is much harder to find. Partition also exists very prominently in the library, and it has an A to bool, and it gives you 2 lists back, a pair of 2 lists. And again, you have to know which one is which. So actually, like the first one, I think I have to say right now, is the one of all the elements that satisfy this test, and the second one is the one of all the elements that fail the test. Okay, but better would be if we had a partition function that would go from A to either B, C, where we say like, okay, we actually make a binary choice, and we either provide evidence of one outcome of type B, or we provide evidence of another outcome of type C. And now it would be completely clear from the results are, because it is a list B and then a list C, which one is which, right? Sorry. Okay, so now to get to the end, let's revisit the beginning. And obviously, I mean, in a real program, we're most interested in real examples. And as I said, I think there are really many of these kinds of examples in real code where you perform some checking, some kind of validation on some kind of value, and you have the opportunity to provide evidence. But often the checks you're performing are far more complicated. And we have now seen, okay, sure, for a non-empty list to say suitable evidence is to store the first element of the list and the rest of the list. That is kind of obvious, perhaps. And for an even number to say, okay, we store the number divided by 2, that is still kind of obvious. But what would be suitable evidence for a complex textual check as to whether something is a valid email address? Do we actually like sort of parse this and store an abstract syntax tree? Well, okay, that would be one option, but you can imagine yet more complicated things, and sometimes that may just not be what you want, and sometimes it may actually introduce performance overheads that you don't want, because an abstract syntax tree perhaps has a less compact representation. And you don't really need all that complexity, or you don't really want all that complexity in your program just for a little bit of extra correctness checking. So And perhaps the test is even more complicated, and it's just not obvious what the evidence is. So what is suitable evidence for a complex validation? Now, the good thing here is that the answer is actually surprisingly easy. You don't really need to make a very strong distinction here. You already get all the benefits, essentially, if you are taking a completely pragmatic and lightweight approach at that point by simply saying, we're going to say an email is still a string internally, and it is still actually the actual string corresponding to the email address, but we are wrapping it up in a new data type, and we are making that data type abstract, and we're guarding its interface, right? And so that has essentially all the advantages that we need. If we needed, an email is isomorphic to the string type, so we can, for example, easily turn an email into a string again by just extracting its contents, right? But we have full control over the interface of email. Email is treated as a different type by the type system from string. We have to explicitly coerce, and we can hide the coercion function. So we can say, even though make email is a constructor that allows us to take a string to an email, we simply don't make that available to the general public. The only function we do make available to the general public is valid email, which performs the check. And then we still have the responsibility to implement this one check correctly, but that's something that we ought to do anyway, and it is relatively clear where the risk now lies. And if we have a clear, controlled interface to such an otherwise abstract data type, then it basically serves all the purposes that we want, right? We can say, if we have an email address, we know it must have been obtained by running isValidEmail on it. There is no other way to even have obtained it. We can rely on that check to have run if we get a value of this type. And we have a limited amount of operations that we can do on it. So we cannot just concatenate two email addresses, for example, just because we can concatenate two strings, because email addresses are an abstract data type. So there is still no danger of forgetting the test. There is still no danger of duplicating the test. And we don't need to actually be extremely creative in coming up with actual evidence. This sort of lightweight approach is actually enough. Okay. So I'm coming to the end of my talk. So how to win? So how to improve your programming? Whenever possible, replace Booleans with types that actually carry evidence, right? So maybe types, some types of any sort, either types, whatever. And then introduce new types for values that have passed tests, even like in the case of email, if their internal representation does not actually change. Wrap them up in something new, make them abstract, guard their interfaces, make it clear that you cannot, cheat. That I mean, cheating within limits here by choosing the same internal representation, but then make the interface of that type really limited, so that there is just the only option of obtaining these types and maintaining these types and combining these types are operations that you have carefully checked to maintain the invariance. Okay, and generally avoid functions that have implicit assumptions about their inputs, where you say, I take a string, but I expect the string to be of this and this shape. And then you don't know whether the caller has actually respected this or not. And where you don't know whether you have to run a test again, or whether you can just assume that the test has already been run. And avoid unclear boundaries between untrusted and trusted values. And avoid situations where just flipping around a couple of cases in your program would still make the type checker go, yeah, okay, right, we can try this, right? Always, if you see this sort of stuff is like that, you make a really tricky consideration. Is it this one or that one? And they're actually both of the same type, then there's already a signal that something is wrong with your code and you can do better. And if you follow this advice, then you generally avoid these things automatically. Okay, so as credits, let's just say that this is not my idea, of course. I mean, the idea goes back, I think, very, very long ago, but it is coming up under different names and is promoted every once in a while again. I personally really learned it. I learned it in the sense that it was really driven home to me by Conor McBride, and I think around the year of 2005, briefly after my PhD, under the slogan "Learning by Testing." So learning, like if you perform a test, you don't want to get a Boolean outcome. You want to get evidence. You want to learn something from it. Bob Harper, programming languages researcher, wrote a famous blog post titled Boolean Blindness, right? So that was in 2011. So that is a slightly different term again, but the idea is, again, like Booleans are just not particularly expressive. If you have a Boolean, you're kind of blind to what's really going on, at least the machine is. And Alexis King wrote just recently in 2019, wrote another rather influential blog post that's called Powers Don't Validate, where she's saying validation is essentially this process of making a Boolean check. Parsing is like by producing an abstract syntax tree, but if you look at parsing in the wider sense as just something that takes an unstructured input and provides some evidence, that is the thing that you really want in most cases. Okay. I have one bonus slide, but I think I'm basically out of time, or we should come to an end. I just want to say, if you go to dependently typed languages, and in dependently typed languages, you can mix terms and types, you can provide even far more interesting evidence. So, for example, if you look at an equality test in a normal programming language, that will give you a Boolean result, and it will say, I'm looking at two values of some type A, possibly with some constraints, right? So I mean, perhaps not for an arbitrary A, and it will ultimately give you a Boolean. It will just say, yes, these two values are equal, or no. But wouldn't it be nice if we actually had a proof after performing this test that, that the two values are equal, and that we had a proof that the two values are non-equal if the test fails? And in a dependently typed language, you can actually write something like that. And dependently typed languages are up and coming. I don't think they are quite production ready for industrial use, but they're certainly being researched on, and you can do very interesting things with them. And languages that fall in this category are Agda and Idris and Coq and Lean, which are also like primarily intended to be theorem provers or proof assistants, but the distinction blurs a little bit in this area. And this is a fascinating area of languages where you can like do really nice things with this sort of approach and drive it even further. Okay, that concludes my talk. Are there more questions right now?
Yeah, there's a couple of questions. One general question is, do you see evidence-based programming as one aspect of explainability in computer science, artificial intelligence, etc.?
I can't say that I'm really an expert in artificial intelligence, but I do think that one of the big challenges in artificial intelligence is indeed that we want AI algorithms to like get away from just saying yes or no, right? Or even to just say that this image shows a cat and this image shows a car, but to actually give reasons as well and provide evidence as well, so that we can like check why they've actually come up with the conclusion and how far we can trust it. And I think that in that sense, there is certainly scope for this there as well. I just think because of the nature that AI algorithms work, you'll need to do completely different things to actually come up with that evidence. But it's certainly a good idea in general and in that area as well. Yeah.
Yeah, and one follow-up question to that is if you see any connection to proof carrying codes.
Yes, that is a very direct connection. So the idea of proof carrying code is indeed that I think in the widest sense in compilers, but even compilers, I mean, essentially compilers are programs that translate one language into another. But but almost every program translates one language into another. For example, a web browser, right, translates HTML and CSS and JavaScript into some rendering instructions for a rendering engine. So a web browser is a compiler. So I mean, so like lots of things are compilers. And the idea of proof carrying code is that like whatever target language, which can be domain specific and everything you're producing, is carrying some additional proofs about its correctness, relating it back to its input, and also justifying its own internal consistency. And that is very much in line, like, as essentially just a different viewpoint of what I've just said. Yeah, I mean, and again, I don't think it's sort of totally black and white. You cannot say you have to do this everywhere all the time, and you have to like apply a certain amount of pragmatism as to how far you usually want to push it. But so the point that I'm making in my talk is primarily actually a relatively pragmatic one, that you really can get a big payback for relatively little effort if you just are disciplined about like guarding the boundaries of your application code. Proof carrying code, like the research community, is typically a much more serious approach, in the sense that you want to have like full reliability and actually want to be able to reconstruct everything under any price. So the emphasis there is probably slightly different, but the basic idea is very much the same. Yeah.
Cool. Thank you so much. I at least learned a lot from his talk. I hope everyone else did as well.
Yeah, I hope you all have a successful contest. Tomorrow is the real run, right?
Correct.
Yeah. I wish you all the best for it, and I hope that the organization goes well as well, but also the participants, that you all have lots of fun and manage to have good results. And who knows, perhaps you managed to avoid a hard to debug bug in the last 10 minutes by applying at least this technique. I don't think you are allowed to use Haskell, but you can still try to apply the idea.
Correct. The ICPC does not allow Haskell, but actually, as I pointed out to someone in chat earlier, if they want to hone their Haskell skills, we will actually host a public version of the contest next weekend, which will be hosted on OpenCatis. And OpenCatis allows Haskell as one of the programming languages, so you can redo all of your solutions again in Haskell if you feel like it's perfect opportunity.
That's a great, that's a great initiative, and I think in general, I mean, like, I think like learning new programming doesn't have to be Haskell, but just trying out new languages is always widening your skill set and also giving you new viewpoints on old problems. So that is always worth doing. Yeah.
All right. Okay. Thank you so much.
All right.
Feel free to watch the live stream tomorrow, see how the competitors do, and even join another competition yourself if you feel like it next weekend.
Yeah, possibly.
Thank you so much.
We'll see. I have been participating in the ICFP programming contest a number of years, so that but not so much in others. But yeah. Okay. Thanks again.
Yeah.
Bye for now.
Bye.